this enterprise, and I'm going to be doing a presentation on a coordinate system we developed this summer. We call it Pseudodometry. I'll get into that a bit later, but let's just start off the presentation with a bit of basic information. What is a coordinate system? So it's essentially a method to determine the location of an object in a defined space. In this case would be the field. There are many types. There are Cartesian, which you may know from algebra, pretty much XY plane. There's also a polar, which is essentially your heading, which pretty much, and they both identify the distance from a point of reference. Now you may notice that the polar is more in terms of angle rather than in terms of position, but that's useful later on when we want to find our heading. So what is the advantage of using one in FTC? So the advantage of using a coordinate system is that it's simpler to program. It's way easier to plan your autonomous. You just measure the points you want to go to and the robot goes to them. Adjusting things is a lot quicker. Movements don't stack up on top of each other. You can just adjust a movement and then it will go to that position no matter what you did before. And also it can create shorter movements, and that allows for quicker autonomous, which allows you to do more stuff, which is always good. So what is pseudodometry? So it's very similar to odometry. That's why we call it pseudodometry. But instead of using external encoders, we're actually using the encoders built into the motors. And we're using both a Cartesian and a polar coordinate system. As you can see on the sketch from one of our notebooks, we're not only are we using the position in a Cartesian plane in the XY direction, but also our heading in the polar plane. So this requires a lot of trigonometry. So if you weren't a big fan of trigonometry in school, then maybe you might want to have a bit more enthusiasm. So what we need to do this, we need Encoder Drive, which can be found very easily. It's one of the examples in the FTC SDK. Encoder turning, I'll get into that, but that's also very easy. Angle finding, which is just a bunch of trigonometry, and a run to position method, which essentially ties in all our encoder drive, encoder turning, and our angle finding. And that pretty much consists the whole system. So the encoder drive is very basic. It's found in the internal examples of the FTC SDK. And it's pretty much the base for moving anything with encoders. You can see here that it's essentially, you're just calculating with how many counts per inch you have in an encoder. So you have like, you take the diameter of your wheel and then your circumference of it, and then you know how many counts you'll have each inch that you're going. And then you just set that as your encoder's target. You set power, wait for it to reach the target, then you just cut power to the motors. Super simple. Now we're going to go to something a bit more complex, but not too complex, is encoder turning. The code is nearly exactly the same as encoder drive. The issue, the single thing is that you need to calculate how many counts per degree, because you're still moving, but except each side of the robot is moving in opposite directions. That's how you turn. So essentially, we could do a bunch of math to do this, but my preferred method is we use the built-in gyro, and then we just go to a bunch of angles and average them out, and that works really well, surprisingly well. And I didn't have to do any math for that, or any complicated math for that. So, and then finally we have our angle finding method. So this is essentially a lot of trigonometry. So it is the most complex system, but if you know your way around trigonometry, it's fine. It's essentially finding out how many degrees you have to turn to reach your point, because since we're using the motors in it, we can't really strafe, but this is good if you don't have Mechnum wheels. So you're going to be able to turn and then go to your position and then turn to your wanted heading, and you're going to use this get angle error method. It's essentially just finding the triangle that you need to move that brings you to your position. You take the hypotenuse of that, that's your distance, and then you need to find what your angle is to turn from your current angle to that angle. And then we just have some if statements to handle some different scenarios, and then we'll just return our error. So, and then they'll send that to our encoder turn method, which will then turn it. And then finally, we have our run to position method, which essentially calculates our hypotenuse, turns the robot to the specified angle. Then we move it the distance of the hypotenuse, and then we have to calculate our wanted angle. So because you're moving to a specified point, your angle might be a bit wonky. It might be like 3.97 degrees and you want 0 degrees. So then you can put in 0 or 90, and then it'll just do the same thing as before and calculate it, and then it'll just turn it. And then we just set our current position. And that's pretty much the entire thing. So if you look at this example, the expected output is going to be turning, then moving to the point, which is the blue dot, and then you would turn again to your final heading. This is a lot quicker than what we were using before, which was moving forward and strafing side to side, having to scan each block. With this, we can actually scan all of them and then go to it, which is a lot simpler. Now, this we have a video that goes into this in a lot more detail, goes step by step. It pretty much goes through the entire code. Here are some links. I'm going to actually paste the video link into the chat. And then that video link will pretty much go through it step by step. And also includes our link to our GitHub, and also some other contact links like our website and our Shutterfly. And if you want to contact us, we have our email and our Twitter on here. So DM us on Twitter if you have a question, or send it to our email. And that's about it. So does anybody have any questions? I know it's a bit short, but does anybody have any questions? I believe that they said before that this will be posted on YouTube, this recording. So.
Hi, can you hear me?
Yep.
Yeah, was wondering what kind of testing did you do did you build everything and then run this, create this, or did you how did you, before you built everything, did you do some kind of testing to figure out the best algorithm to figure out how this is going to work?
Yeah, so essentially the story behind this was that we had our robot ready for competition, and then the quarantine happened. So then the robot ended up at one of our team members' houses, and then we already had our robot built and we knew what we wanted to do. So we got to work like brainstorming ideas on how we could implement a coordinate system without having to buy odometers. And we came up with this idea, which was a pretty basic idea. We just said, what if you just what if you just have a method that automatically turns to an angle and then runs to the position? So we came up with the idea, we developed it. We went through a lot of trial and error. We were a bit off on our trigonometry in some areas, so we were turning like strange angles or doing like full 180s for some reason. So we got some of those ironed out, and then now it is working pretty well. And right now we're more, we've been fine tuning it, trying to get like a base, we have a basic autonomous working, and we're just trying to get it fine tuned so that it's more repeatable. There are a couple of errors that we've ironed out over time that have popped up with like it not turning enough or going too far. So, but we got those ironed out and it's working pretty well. But yeah, that's essentially how we developed it.
Did you guys set some kind of accuracy requirement or success criteria on when you thought that was fine-tuned enough, or what did you guys go through to figure out what was good enough?
Yeah, our criteria was essentially get something that was more accurate than what we were using before, which was just moving in a straight line with Encoder Drive. And our main point was the sky stones. At the beginning of the match, we would scan the sky stones and move. The biggest issue with Encoder Drive, sometimes we would just ram straight through the sky stone and push it back like 3 inches, and sometimes we would come way short. So our goal was to get it accurate where it was repeatable within, I think we said 80%, where 80% of the time it would be in the exact same position. And from what we saw, it is in the exact same position about 85% of the time. The other time's a tiny bit off, but not enough to really screw up an entire autonomous. But that was really our accuracy goal, was about 80% of the time going to the same spot, and then try not to ram through blocks. So that was our goal, and that's what we achieved.
Thanks.
I think the next question is from Vivian. What if you don't know trig?
There's a thing called Khan Academy. Wait, how
Excuse
could you? Yep.
My name is Vivan, not Vivian.
My apologies. Sorry about that.
It's okay.
All right. Do I answer that question or?
I think the next question is, how do you?
It's Code Academy?
What?
You were saying it's in Code Academy?
Yeah, so Khan Academy is like, it's online learning. So you can just go on, you search Khan Academy, and they can search trigonometry, and they have all the resources. That's pretty much how I learned it, and at school also. But it really helps.
Thank you.
Yep. And the next question looks to be, how do you calculate the counts per inch when turning?
Yep. All right. So I go more in depth in the video, but I'll go through it right now since we have a ton of time. So what we did essentially was we created an autonomous that would essentially use the built-in gyro in our rev. The issue with the gyro is that it's very accurate, but it's pretty slow to update. So then if you're moving fast, you might overshoot it. That has to go back, and it pretty much spends a whole bunch of time ping-ponging back and forth. So so what we did is that we just made an autonomous that would turn to, I think it was 15, 45, and 90 degrees, and then we divide them so that we get, and then we save the counts from each encoder. We then averaged them to how many counts per degree, and that got us to, I can't remember the number off the top of my head, but it got us to how many counts per degree we got, and then we just used that instead of counts per inch was counts per degree. So then whenever we want to move 1 degree, we go that many counts in the encoder. But essentially it was just an autonomous that we ran one time, and then it just displayed in telemetry the number that we needed to put in for counts per degree.
Next question is, how would you utilize Inbuilt Gyro? You mentioned in Java. Is it located in the expansion hub?
Yes, it's in the expansion hub. There is an example code, I'm pretty sure, in the FTC SDK using the gyro. That's what our gyro code is based off of, but we're using the one built into the Rev Hub. All right, any other questions? Oh, I see there's one question. What is the primary thing that Pseudoodometry is used for in FTC? The primary thing would be moving it around. It would be positioning a robot on the field accurately, because what most teams are using, or they started off with, was pretty much just move in a straight line, and then it's all sort of relative, where a coordinate system is more of a absolute. So if you know anything about G code, would be the difference between G90 and G91. So you'd have an incremental where it's like move 1 inch, move 1 inch, move 1 inch, or absolute where it'd be move to 1 position 1 and then move to position 2 or whatever. So that would be the biggest difference between like just moving in a straight line versus keeping track of your position on the field. Would you recommend this method over traditional odometry? If you don't have a mechanism drivetrain, traditional odometry can be a bit more difficult since you can't strafe. So this one is pretty simple. You don't need any extra encoders on the side, and the code is just some basic trigonometry with the example codes. So if you had like a tank drive, I think this would be pretty good. If you have a mechanism drive, I would consider looking more into odometry since that'd be a lot quicker to move because you can strafe, and it's a lot more, I would say it's a bit more accurate than using the encoders and the motors because you always have the risk of a motor slipping and then losing count. So I would say traditional odometry would be the way to go if you have a mechanism drivetrain. A tank drivetrain, you would probably want to go for a method like this.
Do you notice a lot of slip between like the wheels that you guys used and the foam mat? And how did you, if you did see a lot, how did you accommodate for that mismatch between what you got from maybe the reading from the encoder versus how far you actually went because you were slipping?
Yeah, so for us, slipping wasn't a big issue, but how the encoder drive works, it takes the readings of all the wheels, and then if I can't remember exactly the logic, but I'll go back to that slide. Here you can see while op mode is active and runtime, that's just like a timeout. Then your telemetry, or no, not the telemetry. So if both drives are busy, so that means that if both motors are trying to reach their target, even if one of them has reached their target, and the other one is still running, it's still going to keep on going. So the rare, I would say it's pretty rare that you'd have 4 wheels slipping, or 2 wheels in this case. But if one slips, you can still reach that point. In terms of turning, we haven't quite figured that out yet, but you could probably use the gyro to just try and keep your heading, which I've seen teams do before.
Just for information, the code for this room is unicorn, and I'll put it in the chat also.
All right, I'll just leave this up if you want to copy this down. Again, if you have any other questions or inquiries, then just make sure to email us. All right, well, thank you for listening to my presentation.